Hello, good morning everybody. Thank you for joining the machine learning session today. It's my pleasure to invite the speakers of three great talks. The first two people that I would like to invite to the podium are Abdulrahman Ali and Ajit Suresh to present a paper on Fatemeh Ganji MPC, close to my heart. Topic is related to application of MPC. The floor is yours.
Thank you, and good morning everyone. So today I'll be presenting, actually we will be presenting our work, FANG MPC. It's a framework for artificial neural networks and generic MPC. And I'll introduce my wonderful co-authors in this collaborative work. So this is a collaborative work with our institute, TII, Technology Innovation Institute, and Bochum University. Coming to the motivation, the table here actually shows a summary of the PPML frameworks. By PPML, it's privacy preserving machine learning. And of course, it's a disclaimer that this table only represents a subset because the area is very hot and there are like a lot of works happening in this area. And the main challenges when we come to a privacy preserving machine learning framework is first the reproducibility crisis and the prototype implementations. That means most of these works are focused in an academic sense, in the like they will come up with a protocol, the theoretical protocol, and often associate with a prototype implementation and sometimes not even an implementation. And they cover various settings because if you are aware of multi-party computation, which is our backend, it has various settings like the number of parties, the number of corruptions that it can tolerate, like that. So we have like two-party setting where there are only two parties, which we call as dishonest majority because there one party can be corrupt. And then there is two-party plus helper, then three-party, four-party, and finally like the n party, where these 2, 3, and 4 are the most common ones in the literature. So because of these various settings, it's often hard to have like a fairness in the comparison because they are like different protocols with different implementations. So it's like if you just take their numbers as such, it is like comparing apples with oranges. So it's always good to have one framework where there is a support for different protocols. So that is exactly what we tackled in this FANG MPC framework. So a platform to support variety of protocols. And the setting that we focus is the dishonest majority setting. So the dishonest majority setting means in a setting of n parties, up to n-1 parties can be corrupt, which is like the strongest setting that we consider in the domain of multi-party computation. And we focus on the strongest corruption model also, which is called malicious or active security. That means in malicious corruption, the adversary or the corrupt people can deviate from the protocol. So that's the strongest threat model that we consider. So basically, we consider the strongest threat model in two different aspects. One is the number of corruption, we take up to n-1 corruptions, and one is the nature of corruption, which is like the threat model or like how the adversary corrupts the parties. So in this table specifically, the particular setting corresponds to two-party dishonest majority, even though our framework supports n-party dishonest majority. But in the summary of works, it only covers the two-party dishonest majority setting, which falls in this setting. And in general, any n-party setting with dishonest majority corruptions. The other ones in these tables are actually on weaker settings. And when we propose a framework, of course the question is like, okay, aren't there any other frameworks available? Yes, there are a couple of frameworks. These are all MPC frameworks, like the frameworks for multi-party computation. The MP Speeds is a popular one, then the Scale Mamba from COSIC. Then Facebook has Crypten, which is like again a PPML oriented one, but that is on three-party specifically. And the Encrypto group has Motion, then Microsoft has ECPC, then there is a EMP toolkit, and there are like several frameworks available. And we chose to build our privacy preserving machine learning framework on the popular Scale Mamba framework. So Scale Mamba is one of the earliest MPC framework, and it's specifically designed as an MPC framework as such, because at that time it was not like privacy preserving machine learning was the application of focus during that time. So this is a framework that is basically designed with a practical implementation in the mind. That means like the implementation is more close to a real world implementation. So it considers all the aspects which we will see in the subsequent slides. So coming to the positive sides of Scale Mamba, for specifically privacy preserving machine learning, has a ready-to-use domain-specific language, and it already supports various protocols with active security, which is the security model that we tackled, like around 18 protocols in different settings. And by that time, when we adopted, it already has the support of Boolean circuit evaluation in the malicious setting via the protocol HSS 17, and it has a robust architecture that is more close to a real-world implementation. Now, when it comes to the negative side of Scale Mamba, explicitly for the privacy preserving machine learning, it was not designed for privacy preserving machine learning. So as a result, it cannot compile large programs. Okay. For instance, when it comes to privacy preserving machine learning, the programs are very large, and for instance, it cannot even compile greater than 2 power 32 bytecodes, and it didn't have a decoupled pre-processing phase. So in MPC, we have various way of execution to leverage the so to obtain the maximum efficiency in the online. What we do is a phase called pre-processing, where we do some input independent computations beforehand so that we can get a fast online time. So in Scale Mamba, even though there is a pre-processing, but it does not have a support for a decoupled pre-processing phase. By decoupling, we mean like, okay, we can do the pre-processing now and store the results, and later when we have the actual computation, we can use them. That's the decoupled pre-processing phase. And it had the limited I/O because it only provided console access by default. And it's neither pros nor cons, like it didn't have specialized ML libraries like for the privacy preserving machine learning. And unfortunately, it's no longer maintained, like they stopped the support earlier. And even though it has the support of this HSS 17 protocol, it was not an optimized implementation. So it requires like much more communication and cost to realize that protocol. So coming to our contributions, what we focus is on privacy preserving machine learning inference, and this is like a high level summary of our engine. So basically we have a ML inference engine, and it has a client. This is a demonstration with respect to two parties, okay, a client and server, even though the framework supports n parties. So there is a model owner with the neural network parameters as its private input. There is a client with its data as its private input, and both will submit to the ML inference engine privately. And we have a pre-processing engine which generates the pre-processed material, like the input independent material, and provide to the engine, and it will do the computation, and finally the result of the computation will again be like in two secret shares. And if you combine the secret shares, you will get the final result, whatever be. For instance, with respect to inference, it's maybe like a query as the input and the classification result as the output. So both the secret shares will be given to the client, and the client can obtain the output. That's the high level architecture of FANG MPC framework. And as I mentioned, it covers dishonest majority plus active security, and it has a dedicated and deployable pre-processing. So in the context of multi-party computation, we have a couple of this correlated randomness. The correlated randomness means the materials we want to generate, which are input independent, and that can like speed up the online phase. So it has support in a field arithmetic as well as in the Boolean domain. And one distinct feature of our framework is we usually in an MPC protocol, if there are like two parties, then they will only be like doing the pre-processing, and they will store the result, and later they will use it for the online. Okay. So in FANG MPC, what we envisioned is like this pre-processing can be using a different technique altogether, not just simply secret sharing based MPC. So as a result, what we did was we allowed pre-processing by a distinct set of whom we call as dealers. Okay. So we can choose from a pool of dealers, and they can use their underlying technique. For instance, in FANG MPC, we focus on fully homomorphic encryption, and they can generate the pre-processing material, and we have a unit that will take this data, and we can later use it for our online phase. I'll come into more details of this in the couple of minutes. And coming to the machine learning optimizations, we have like ReLU, which is a activation function in privacy preserving machine learning. We combine it with another operation called truncation. This truncation is basically like, okay, when it comes to privacy preserving machine learning or machine learning in general, the underlying values are floating point values. Whereas in multi-party computation, we work with either a field or ring, which is a fixed algebraic structure. So we need a compatibility between these two representations, and we use something called fixed point representation that allows you to take floating point arithmetic and do the operations on the underlying ring or field. So, and that requires some operation called truncation for like operating on this. And we have a support for specialized ML libraries. And the implementation is open source, and you can avail it in this particular link. And coming to the FangMPC framework, I'll quickly go through the 5 different modules of FangMPC framework. So first is a dealer module, and as I mentioned, the dealer module has support that a distinct set of dealers can generate the pre-processing materials, and we specifically use the FHE based scheme from these works, CMR20 and MG23. And also to achieve the malicious security, we use zero knowledge proof of knowledge from BCS20. And next is the converter module. The converter module is responsible for taking the material that the dealer module generated and convert it in a form that the online module, which is actually executed by a different set of parties. So converter module is basically responsible for making this transition. And in addition to the dealer module, we have a dedicated pre-processing module that is carried out by the online parties itself. So they will be doing some other calculations other than what the dealer computed for them. So that is taken care by the pre-processing unit. And once we have the pre-processing computed, we need a way to store them so that we can use it later. And for that, we added support via storage unit. So in the storage based one, we have support for either file system or database for the storage. So we can choose which way to store the preprocessed material, and we can later retrieve it during the online stage. And finally, with these 4 components, we have the evaluation engine that contains all the implementations of the underlying ML libraries, and it will do the online phase when the actual input, which is the model parameter, and the query comes into place. So I'm quickly going through the architecture, and finally the architecture looks something like this, where all the 5 modules are there. The dealer module is there, and once the dealer module generates the pre-processing material, it goes to the converter module, and then it stores to the storage support. And in addition, or in parallel, there is a pre-processing unit that will generate the other set of pre-processing materials, and that will also be stored to the database. And once the online evaluation starts, the client and model owner will retrieve their corresponding secret shares from this storage support and use it to compute the evaluation engine. So this is the overview of the entire FangMPC framework. And now I will hand over to my colleague Abdul for the rest of the talk. Thank you.
Well, hi guys. Thank you for coming after the ROM session. I know it's tough, so thank you for being brave. So just for that, I'm going to take 2 hours of your time and speak non-stop. Okay, so thank you, Ajit. He gave us like a big overview of what we wanted to achieve. The real question that we wanted to ask is what we need to actually make these protocols and these frameworks usable in the real world. So sometimes we hear and we read on papers, well, you know, you just have to do this. You know, it's simple. We wanted to see what that simple actually meant. Okay, all the stuff that is left for the reader as an exercise, we wanted to try to explore it. Okay, so one of the common things that we got was why you guys are not doing the garbling offline. As Ajit explained, we use a variation of HSS 17 in the framework, and what it does, because of reactivity, it garbles every gate on demand. So whenever there is a call for a gate, it garbles the gate, it executes the gate. That's a quite expensive operation to do online. And we get queried a lot, like, okay, guys, why are you doing this? There is not another more practical way to do it. We said, yes, just give us 3 more years and a couple of slots on your conference, and we will do it for sure. So we decided to try to investigate it, how to actually achieve it and implement it. So there are two challenges, and a simple way to solve it is that sadly operations that are executed with this kind of protocols, they need to be interlinked via the choice bits that you use for the base OTs, for the OT extensions. So we persisted them, and we recovered them on execution time. And then we try to use our persisted circuits and our persisted choice bits on the evaluation of real convolutional neural networks and see what happens. Okay? A second item is truncations. Truncations are a huge bottleneck in the PPML literature. Everybody wants to try to find a way to actually get rid of the truncations. So in this work, we try to actually do something that is kind of insinuated in the literature, that is, okay, like the truncations have a similar workflow as the ReLUs, so they should be easily intermixed. So we tried that. We took two popular protocols for comparisons and ReLUs and for fixed point arithmetic, and we tried to mix them and see what happens in reality. So the result was the protocol you're going to see now. We construct some masks in a fairly specific way using authenticated bits that are typical in the literature combined with DA bits, and we create a super funky mask. That's the mask that you see there, that you of course all understand because it's clear as water. And then imagine you start doing your convolutions, and like you start accumulating multiplications and operations that actually need truncation, but you don't do it. You just let it be accumulated. And at some point, you decide, okay, it's time to do my ReLU. So you take the value that you have accumulated, you mask it, and you open it. And because of the properties of both protocols, it turns out that if you build the mask in that way, you can actually do it to do the truncation and the ReLU in parallel. So the truncations, they come for free. Okay? So I'm almost at the end. So congratulations, you survived. On the results, as Ajit said, this is our test bed that we use for our testing. We tried with LINET, we tried with ResNet 18 and BGG 16. We tried on different setups. We tried on full threshold 2 parties. We tried Shamir 3 parties. We tried also full threshold 2 parties, but we eliminated all the ReLU stuff that you saw. We just used polynomial approximation. And then these are the results that we got, that at the time they were quite good compared with the state of the art, given that this is actively secure and using the realization of the offline model, the first that we know of. Okay? So this is basically what we did. We managed to have some ecosystem built around common use MPC frameworks. We actually have real dealers that they give you shares that you can of correlated randomness that you can later use, and we build cool machine learning libraries that you can also reuse if you want to. Okay, and we fix some bugs on Scale Mamba too. Yeah, that took some effort. What we would like to do, like we would like to revamp the GC evaluation engine. This is something that neither MPSPITS or Scale Mamba had or have at this point, and it's the ability to try to evaluate garbled circuits in parallel. We also realized that although in theory you only have a constant number of rounds, given the amount of gates and the size of these circuits that you evaluate, they are actually not being executed in a couple of rounds. TCP doesn't work like that. So, and that's it. Thank you. These are the citations. And this is the paper. And no, I'm kidding. Yeah, that's it. Thank you so much.
Fantastic. Any question from the audience? I know it's too early in the morning, but microphones are on. please use them. No questions? Great. Then I can ask all the questions that I have noted here for you.
Please.
So, in the first part, you mentioned that you have malicious adversary. Do you recall what type of malicious adversary it was? Is it like selective OT or input inconsistency? What type of malicious activity your malicious adversary can do?
Anything, yeah. Technically anything.
So let me put it in this way. Is it just a malicious adversary that you can resolve by just including the cut and choose? Cut and choose will resolve the issues?
So you are actually mentioning about specific attacks launched by malicious adversary, but in the multi-party computation, when we say like, okay, we have support for malicious adversary, that means all these attacks are covered. It cannot do any attack, okay, that are listed in the malicious act. So it supports all.
Okay, I think we can take it offline because we can make it more specific. And then Scale Mamba, does it support malicious adversary in the sense that you want?
Yes, it has, from the MPC perspective, from the multi-party computation perspective, it has support for malicious adversary.
And
so,
it was equipped with cut and choose.
Again, like yes, it has cut and choose, but that's one way of achieving malicious security for a particular attack. Okay, so it has to take more into account. That means like when we say like, okay, protocol has support for malicious adversary, it needs at least the verification mechanisms to prevent any kind of act that makes the corrupt parties deviate from the protocol. So cut and choose is just one technique, and that is specific to one set of protocols. Okay, whereas for instance, if you go to a three-party setting where we use Shamir sharing, that is not the technique that we use to prevent malicious activity. So we have something like the polynomial-based correlation checks that are employed because this comes as features of Shamir secret sharing. So like I said, so these are general MPC frameworks which has like support of wide variety of protocols. For instance, specifically there are 18 protocols that are immediately supported, and each one comes with its own set of the way of preventing the malicious ones.
So the backbone for malicious support is coming from the secret sharing?
Yes.
Okay. And the dealers, they are non-colluding, right? Based on the assumptions that you are making.
Honest majority. So, so as long as one of the dealers remain honest, is okay.
Okay, one honest is enough.
Yeah, it's like we follow again like the dishonest majority setting in the dealers also. For instance, in the current implementation, we like immediately support up to 10 dealers where you can choose the pool of dealers. Okay,
cool.
The client can choose from the pool of dealers. Okay, these are the dealers I want, and as long as there is one honest dealer, it's secure.
That's cool. And this is also supported by Scale Mamba.
No, it's
you added that.
Yeah, it's
cool.
based on homomorphic encryption.
That's
it's a
nice.
Different.
Wonderful. Now, any follow-up on what we discussed? That was a warm-up. Okay.
Thank you, everybody. Thank you for coming.
We can thank the speakers again, and I would like to invite the next one to the podium. Next, we have a presentation by Jonas Sander, and it is related to accelerating distributed private convolutional neural network. The floor is yours.
Yeah, so thank you for the introduction, and good morning, everyone. So today I want to present our framework DASH for accelerating distributed private convolutional neural network inference with arithmetic garbage circuits. And this is joint work with Sebastian Berndt, Ida Bruns, and Thomas Eisenbart. So just for you to keep in mind, in DASH our goal will be to distribute the neural network inference workload between a garbling device and an inference device. And because DASH is all about garbage circuits, I want to start with a small introduction to garbage circuits and arithmetic garbage circuits. Then I will present our framework dash, show some results of our evaluation, give a preview of redash, and in the end I have our final conclusion. So to introduce garbage circuits, let's imagine this situation of Bob and Alice, where Bob likes Alice and Alice likes Bob, and both want to go on a date together, but neither dares to ask because both of them fear of ending up in this embarrassing situation where the other one isn't interested in dating. So of course the question is, can we somehow solve this problem? And of course we can. We can just use garbage circuits because they allow two parties to jointly compute a function without revealing their private inputs. So before we can use garbage circuits, we somehow need to model this functionality in a circuit. And in this way, or in this situation, it's quite easy, right? We can just use the AND gate because there will only be a date if both of them are interested in it. So in garbage circuits, to now protect the confidentiality of the inputs, instead of bits on the input and output wires, we now use secret keys. And per wire, there are always potentially two keys, one key corresponding to the 0-bit and one key corresponding to the 1-bit. And the garbage gate itself is then basically such an encrypted table where we use the keys on the input wires to encrypt the keys on the output wires in such a way that it represents the functionality of this gate. So in this case, we should only be able to obtain the key corresponding to the 1-bit on the output if we have both keys corresponding to the 1-bits on the input wires. So in a real setting, we wouldn't know the semantics of the input keys, so we need some method to detect correct and wrong decryptions. But if we have such a method, the position of the correct decrypted ciphertext would directly leak the semantics of the input keys. And therefore, we need to shuffle these entries. And then a quite obvious but not really efficient method to detect such correct decryption would be to just append a random string to the plaintext before encrypting it, and then do trial and error decryption where we just match the random string of the decrypted ciphertext against this public random string. So now we can build more complex functionalities by just stacking up these garbage gates in such a way that the keys on the output wires of the first gates are now the keys on the input wires of the following gates. And we can realize quite complex functions, but we get two problems. The first one is that these circuits get quite big, and the second problem is that these circuits cannot be reused directly. And in Dash, we implemented many optimizations from previous work and also introduced some own ones to tackle the first problem, but the second problem will remain open in Dash. So before we can have a look at the classical garbage circuit protocol, we need another building block. It's called an oblivious transfer. Again, we have Bob and Alice. Bob has some secret bits, B0 and B1, and Alice can now select to learn one of those bits, but only exactly one of those bits and not the other one. And in parallel, this protocol ensures that Bob will not learn which of these bits were selected by Alice. And now we have everything together to build this classical garbage circuit protocol where Bob and Alice can now answer their dating question securely. And in the first step, Bob prepares the garbage circuit, sends it over to Alice. He also sends the input key corresponding to his input. So in this case, he's unfortunately not interested in a date. And he will also send over a translation table that allows Alice to translate a garbage output to its semantic. Then they perform this oblivious transfer in which Alice learns the secret bit corresponding, the secret key corresponding to her input bit. And then she just can run the garbage evaluation, gets the secret output key, and can translate it to the actual output and send finally the answer back to Bob. So in this classical setting, garbage circuits just achieve security against semi-honest adversaries that, or in which the attacker follows the protocol, but is curious and tries to learn private information. So in the past, there were introduced many optimizations to these circuits, and these are the most interesting ones for Dash and also for arithmetic garbage circuits, because as we will see, they somehow generalize. There's point and permute, which allows to evaluate a gate with just a single decryption gate, decryption call, sorry. Then there is garbage row reduction, which allows to garble every gate with just 3 ciphertexts. There's 3 XOR, which allows to garble XOR gates without any ciphertext or crypto operations. And there's a half-gate optimization, which allows to garble AND gates with just 2 ciphertexts. So, as I told you in the beginning, in Dash, instead of answering a simple dating question, our goal is to garble whole convolutional neural networks. And therefore, using these classical binary garbage circuits would result in massive overheads. So therefore, we used something called arithmetic garbage circuits, which instead of keys use labels which directly encode the arithmetic values and much better suit the arithmetic needed to perform inference in neural networks. And these arithmetic labels allow to garble additions without any ciphertexts. They allow multiplication by a constant without any ciphertexts. And actually this free addition is just a generalization from the free XOR optimization. Point and permute is possible, row reduction is possible, and these half gates generalize to quite efficient mixed modulus multiplication gates. So, as we have seen, these linear operations are quite efficient, but garbling arbitrary functions is really expensive, as for them we need to create 1 ciphertext per possible input into the function we want to garble. And this would make garbling activation functions, like for example the ReLU function in neural networks, really expensive. And therefore, previous work already proposed to use these residual number systems, which allow to split up a large value into multiple smaller residues and perform operations independently on these much smaller residues. So additionally, we also need to compute over negative values in neural networks, and therefore we need to somehow encode the sign information in the finite ring that we used for the residual number system and also for the arithmetic garbage circuits. And therefore we just split it in half, use the first half for positive values and the second half for negative values. Now we create a new challenge because to garble activation functions like the ReLU, we need to be able to somehow extract the sign information of an encoded value, and that is not directly possible, as the magnitude information of an encoded value in an ANS system is distributed among all of the used residues. And to our luck, there was already a solution presented in previous work, a sign gadget that allows to quite efficiently extract the sign information in an arithmetic garbage circuit from a number encoded in a residual number system. Yeah, and therefore we just use that one. So let's talk about Dash. So in Dash, next to this classical garbage circuit protocol with just 2 parties, we also allow for more distributed settings, which allows Dash to incorporate even more parties. And we also, like in the work presented previous, we divide the protocol into an offline and an online phase. And in the offline phase, in this example, a model owner would share a public neural network with a garbling device, which then would garble this neural network, sends encoding information to the input owner, decoding information to the result owner, and the garbled neural network to an inference device. And as soon as an input owner wants to run inference, the protocol would transition from the offline phase to the online phase. And then the input owner would send the garbled input to the inference device. The inference device would run the garbled inference and send the garbled output to the result owner, which is able to decode the garbled output using the decoding information and learns the final result. So yeah, that's for the setting. Let's talk about quantization. So as you know, neural networks typically, or at least often, use floating point numbers, and therefore Dash supports two quantization schemes. One quite straightforward one, which we call simple quant, which allows to garble quite small neural networks, and a more powerful one, which we call scale quant, that allows to also effectively garble a little bit larger networks. So let's have a look at how the scale quant mechanism works. So in this case, we have a fully connected layer. And as you see, if we just would apply the scale quant mechanism on the model parameters and on the input, the length of the output would just explode. And therefore in Dash, we introduce a new scaling gadget that we can append at the output of such linear layers, and allows us to keep the value ranges manageable. So yeah, let's see how scaling in Dash works and start with this high-level perspective. And as you can see, scaling unsigned integers is really straightforward, but also scaling signed integers is not too hard. We just need two shift operations. And now we can also see how this works out in residual number systems inside of garbled circuits. And as these shift up and shift down operations are linear, they can be performed quite efficiently on the individual residues of the NS system. And also the scaling can be performed individually per residue, but not for the residue mod 2, as there does not exist a multiplicative inverse. And therefore we need a solution, in this case a so-called base extension, that allows us to determine this residue mod 2 after the scaling operation. And yeah, if we then look at the Chinese remainder theorem, we can see that this residue mod 2 just toggles whether the value after scaling ends up in the lower half of the finite ring or the upper half of the finite ring that we initially used to encode our values in the NS for the arithmetic garbled circuits. So, and yeah, now if you remember our encoding with the positive values of in the first half of the ring and the negative values encoded in the second half, we see that this residue mod 2 just toggles whether the value will be seen as positive or negative after scaling. And as we know, when we scale a number by 2, it should end up in the first half of the ring. We now can just use this previously introduced sign gadget to determine whether the residue mod 2 must be 0 or 1. So this is another main contribution of Dash. Yeah, it allows to run the arithmetic garbled circuit evaluation parallel on multi-core CPUs and GPUs. And therefore we introduced a new data object we call label tensors that successively places the arithmetic labels of these arithmetic garbled circuits in memory. Yeah, it does it layer-wise in the sense of the neural network, and then allows us to quite effectively run all garbling gadgets of Dash in parallel on the CPU and on the GPU. So Dash is implemented in C, C++, and CUDA, It supports dense convolutions, ReLU, sign, and scale layer. And yeah, actually we also implemented an extension with the TEE, in this case Intel SGX, that allows to ensure that this garbling device actually garbles the correct circuit. Additionally, we used OpenMP for the parallel CPU implementation, and Dash supports neural networks given in the ONNX format. Okay, let's have a look at our evaluation. So we started with some micro benchmarks, in this case for thread scaling, and we have one figure per layer type. On the y-axis you see the runtime, on the x-axis the number of threads, and yeah, we found that all these layer types benefit from our parallelization using our label tensors, and nearly every additional thread improved performance. Then we evaluated the speed up we achieved on the GPU. Again, we have one figure per layer type. We see the speed up on the y-axis, and on the x-axis the dimension of the inputs. And again, all layers achieve a speed up on the GPU. But the linear layers obviously benefit most from the GPU acceleration. And yeah, we also found that the approximations that are possible in the sign gadget from previous work can also further improve the performance gain of the GPU. Yeah, but that's just a side note. In the next slides, we always use 100% correct computations. So then we evaluated the end-to-end runtime of Dash using an MNIST and a CIFAR10 model, and found that it is quite fast compared to previous work, except for this model B, where Gazelle is a little bit faster, but yeah, that's really marginal. Okay, then we also evaluated the test accuracy, which we achieved using the garbage circuits, and compared it to the previous frameworks that used arithmetic garbage circuits for inference. And yeah, we found that ScaleQuant quite strongly improves the test accuracy, especially in the case of this larger CIFAR10 network. We also evaluated the communication overhead, and we found that in this distributed settings, where we just need to communicate the garbage input and the garbage output, Dash communication volume is constant and quite small, especially compared to these previous works. And yeah, in the end, we also evaluated the runtime distribution and found that Dash runtime is heavily dominated by the computational workload in comparison to the communication. And yeah, that directly leads us to the next slide. So in the beginning of this year, we already presented our follow-up work at Simla in Munich, where we extended Dash with a generalized base extension that allows to draw scaling factors from the ANS base instead of just scaling by 2. We introduced a more powerful or effective ScaleQuant Plus mechanism, which allows to use optimized ANS bases. We also had a few implementation level optimizations, and again achieved a 33-fold speed up compared to Dash. So now to the conclusion. So Dash is an inference framework purely based on arithmetic garbage circuits. Our label tensors enable efficient parallel evaluation of these garbage neural networks. The scaling gadget allows garbling larger models more effective. And yeah, Dash requires only a constant number of communication rounds, and the communication volume is constant. Okay, that's it. Thank you. And any questions?
Questions from the audience? Please use the microphone.
I've heard myself experts on the very recent on slide 1, we showed first
29? We cannot hear you well, by the way.
Slide 9.
And 29.
Hi.
29.
Hi, does this work? Yes. I'm sorry, I'm very much not an expert, but does accuracy mean that your protected network gives the same answer as the underlying network would give, or is this correctness on the actual test, or what does this mean?
Yeah, so actually when we do not use approximations in the sign gadget, we achieve the same test accuracy as the quantized networks. So they will be worse compared to the floating point networks, but as good as the quantized networks. And as we introduced a new scaling or quantization mechanism, these are the results we get out of it.
Okay, thank you.
Any other questions? So we have time for more questions, please.
Hi, thanks for the talk. I'm also not an expert, so hopefully my question isn't silly. But so this reminds me of specialized formats for quantization and how typically after quantizing the network, there's some retraining in order to improve accuracy. Is this something you've explored with the scale quantization methods you mentioned?
Actually not, but I guess that would be really interesting in the future. Yeah, thank you.
Okay, thank you.
More questions? That means it's my turn. So a follow-up on what we discussed on quantization. Have you tried to start with a quantized network and then garble it and see if the accuracy might be even better?
Yeah, actually before garbling we use our quantization method, but we haven't used any quantization-aware training methods or something like that.
That was what I was saying. So that could improve it a little bit.
Yeah, sure.
And now, so the first question that I have on slide number 18, you had a notation that I didn't get. So, what is L here?
So instead of just scaling by 2, we need more than one iteration of the scaling to make these numbers even smaller after the linear layers.
And this happens all in the offline phase, right? Before starting garbling.
So yeah, the quantization happens in the offline phase, but the scaling must be done online.
Cool. And on slide number 25, again on garbling, I had a question. 25, you mentioned something that I didn't get. You said you can ensure correct garbling. And how so? What is the order of using these ingredients, or how is it possible to ensure correct garbling? I didn't get that part.
Yeah, sure. So we additionally introduce, of course, some additional assumptions. So we now need hardware-based security assumptions, but then we can basically attest this garbling device that performs the garbling of the neural network using Intel SGX and remote attestation. And in this way, yeah, we basically ensure that the garbling device does not do something bad and produces a garbage circuit that does not match the neural network.
That's fantastic. But have you also considered using extension to malicious adversary? That issue can be resolved all by itself. So without using a T, then you can attest what type of network is being garbled. Have you considered that, the cost or anything like that?
So you mean using cryptographic methods to make the network or the protocol malicious secure? So we have considered that and described it in theory in the paper, but we haven't implemented it, and I guess it would be really slow for these large neural networks or these large arithmetic garbage circuits.
That's cool. So we can take it offline, just for the sake of saving time. Thank you very much. Another round of applause for the management.
Thank you.
So the next speaker, and that's the last talk of the session, I would like to welcome Han Xia to talk about C-Flame. The floor is yours.
So, thanks for the introduction. So I will be presenting this paper on behalf of the authors because they can't attend. So forgive me that I'm not really familiar with this. So I'm going to talk about the communication efficient secure aggregation protocol for federated learning against malicious entities. So its name is C-Flame. So this is the outline of our slides. And first, let's begin with the background. So federated learning becomes privacy-preserving distributed machine learning paradigm, in which case all clients keep data locally while uploading the trained model parameters to the server. So FL includes three main phases. So local training, aggregation, and updating. So in a typical FL iteration, clients upload gradients to the server after local training, and the server computes the aggregate of the gradients received to update the global model and broadcast the fresh global model to clients. However, our research shows that model parameters like gradients could leak information about raw data. So the aggregation should be secure. So secure aggregation refers to computing a sum without revealing any individual input. So secure aggregation for FL means obtaining a global model without revealing any local model. So after Google's practical secure aggregation protocol, so many studies have focused on secure aggregation against malicious entities. For example, the client or the server could deviate from the protocol specification to obtain private information, and the client could intentionally poison its local gradients. And this promotes two desirable properties. The first one is privacy in the malicious model, and the second one is input validation. So however, it is difficult to satisfy both to these two properties in an efficient way, and the ELSA addresses all these concerns. So ELSA focuses on a practical model poisoning attack in the FL setting. So malicious clients boost local gradients by scaling up their gradients to a large norm, and the ELSA has two non-colluding servers. Each client shares its gradients to two servers. So server filter out boosted gradients by checking two norm and infinite norm. So to improve the efficiency, ELSA lets clients generate cryptographic correlations to help servers' computation. So first, clients generate OTs to help Boolean to arithmetic share conversion, aka the B2A. The second, the client generates square correlations to help two-norm computation. And third, the clients generate OTs to help two-norm comparison. But sending so many OTs and square correlations leads to heavy communication. So in this work, we decided to optimize communication. And we propose C-Flame using two techniques to optimize communication. The first, C-Flame consumes fewer OTs by switching from Boolean to arithmetic secret sharing, and from Boolean to arithmetic share conversion to arithmetic share conversion. The B2A to A2A. So this reduces the number of OTs by a factor of input bit length. And both clients and the servers benefit from this technique. And C-Flame adopts a random linear combination to batch the second message during squaring correlation verification. So this further reduces server communication overhead. So C-Flame only involves two-party computation. So here are cryptographic tools used for 2PC. So C-Flame uses arithmetic secret sharing between two servers. And the client splits input X into two parts, x0, x1, such that x equals x0 plus x1 modulo p. So when p is 2, this is Boolean secret sharing. So in a black box way, so 1 out of 2 OT is that the sender holds two messages M0 and M1, and the receiver holds a choice bit J, and the receiver will output MJ. So correlated OT is the case that one message equals the other message plus offset delta. A square correlation is a pair of values formed like alpha, the square of alpha, and which helps compute squares for two-norm computation. So when verifying squaring correlations, we can use SPDZ sacrifice technique, though the idea is sacrificing one square correlation to verify another one. And A2A share conversion can convert shares over one field to shares over another field. So B2A share conversion is a special case when P is 2. So here are a simple sketch of A2A and B2A in two-party commutation. So in C-Flame, so clients split their gradients and generate enough cryptographic correlations, then send these shares to two servers. So two non-colluding servers will verify cryptographic correlations and execute 2PC with the help of these correlations. Specifically, each client performs 3 steps. So split gradients by AASS and generate OTs and generate square correlations. And the server interact with each other to perform 6 steps. So including verify OTs, verify square correlations, convert shares to shares over larger field, and compute to normal value and compare to normal value. And the final step is aggregate shares. So the well-studied techniques of Boolean to arithmetic share conversion, so it needs one bit to arithmetic conversion for each bit of Boolean shares. And 1 bit arithmetic conversion needs 1 OT. So Boolean secret sharing views each gradient as a bit string, while arithmetic sharing views each gradient as one element in a finite field. Thus, using arithmetic sharing may benefit from the algebraic structure or properties from number theory to reduce OT speed length dependent quantity. So C-Flame uses arithmetic sharing rather than the Boolean sharing, and the follow-up share conversion should be A2A rather than B2A. So C-Flame optimizes A2A by using quotient transfer. So if using ASS to share X, then we have this equation. So and the goal of A2A is to obtain Y0 plus Y1 modulo P tilde equals X. So if X is even, then the alpha's parity will be the same as X0 plus X1. So alpha is equal to XOR value of least significant bit of X0 and X1. So alpha also needs to be split, so which needs a bit multiplication of 2 LSBs. And finally, the server SB can compute the value YB. So such a technique must assume X is even, and here we make a modification. So we assume that X is greater than the half of P. So we can have 2X minus P is odd, and similarly we have this equation, so where X bars are shares of 2X, then servers can compute the share of Y bar, and note that computing the share of beta bar needs 1 bit multiplication, so which consumes 1 OT. And finally, our servers compute YB by multiplying the inverse of 2 over the field Z modulo P tilde. And we can note that our optimized A2A only consumes 1 OT per gradient, and the number of OTs consumed has decreased by log B times compared to the ELSA. And C-Flame further optimizes square correlation verification. So this is the process of verifying one square correlation by using SPDZ sacrifice technique. So server SB holds shares of 2 square correlations. And server first collectively sample a random value T, and then they open E. And the servers compute their second message, shares of T hat. If the opening result of T hat is 0, the square correlation AD is well formed. Computing the 2 normal value of D-dimensional gradient vector needs D square correlations. Thus, for D square correlations, we can batch the shares of T hat by using random linear combination. So therefore, C-Flame obtains about a half reduction of server communication during square correlation verification. And next is evaluation. So we give the comparison to ELSA. We use 1 cloud instance to simulate all clients, and 2 cloud instances to simulate 2 servers. So here's the corresponding hardware configuration. As we fix the bit length of gradients to 32 and carry out 2 norm computation and aggregation over 64 bits, and we choose listed primes. So this table reports the results of communication. The unit is megabyte, and the first 2 columns vary the number of clients and gradients. The missing value of ELSA means out of memory. So we can see that the communication of a single client of EOSA is about 10.5 times that of C-Flame, and the communication of a single server of EOSA is about 6 times that of C-Flame. So the communication optimization is consistent with theoretical expectations. And we also deploy our experiments on both LANs and WANs and measure the runtime of clients and servers. So according to this table, so when without bandwidth limits in LANs, the runtime of both the client and server in C-Flame is several times higher than that of EOSA. So compared to EOSA, so our C-Flame sacrifices runtime for greater communication optimization. And when over WANs setting limited bandwidth, the client runtime of EOSA is about 2.4 to 2.6 times that of C-Flame, whereas the server runtime of C-Flame is about 1.2 to 1.9 times that of EOSA. So we can see that the runtime of each client in C-Flame increases more slowly than EOSA, and the runtime of each server is almost unaffected. So therefore, C-Flame is more friendly to bandwidth-limited devices, and especially for clients. Next, we split phases of C-Flame and EOSA to quantify our optimization of these phases. So meanwhile, we demonstrate the impact of different gradient bit lengths on our optimization. So we set 8, 16, 32, and 64 base gradients and fix the number of clients and the gradients to 100 and 10,000 respectively. So C-Flame reduces client communication during the OT generation phase and reduces server communication during both A2A phase and the square correlation verification phase. So the larger of the bit lengths, the greater of the degree of our communication optimization. So this is consistent with that of that the reduction of OT usage is a factor of the gradient bit length. And we also combine our C-Flame with the training phase of a specific FL image classification task. So we list the model, the dataset, and the algorithm on top. In each iteration, so each client obtains around 80,000 gradients after local training, and all clients and the servers execute our C-Flame once to compute the aggregates. And the servers broadcast the average aggregates as a fresh global model. So the left subfigure shows that the model accuracy varies with the iterations under the settings of different hyperparameters. So among these 8 settings, so when the local epoch is 2, the batch size is 50, and the learning rate is 0.001, the model converges the fastest. So thank you for your attention. So although I use the term we, but I'm not one of the authors, so if you have any questions, you can contact the authors using these emails. So thank you.
Any immediate feedback on the presentation? So that was a cool presentation, and I hope we could keep in touch with the authors. For instance, I had a question of what are the limitations of this. We are gaining a lot in terms of efficiency, communication costs is not that bad, but what we are missing, perhaps we can read the paper and then get back to them via email. And I encourage everyone to do so if you have a question on this. We can end the session earlier than expected. With that, let's thank all the speakers of the session again, and thank you for coming to the session. Thank you.